2.5b stretches the functions. Okay, so what is a stretch? A stretch is a transformation which results in the distance of the graph, okay, from the x-axis, so from the x-axis is this way, okay, growing by a scale factor of 1 if a is greater than 1, so vertical stretch. Okay, so basically when we stretch vertically, we're stretching like up and down. So what happens is we are getting further and further away from the x-axis or closer and closer toward the x-axis. Okay, as long as we have a factor greater than 1. Okay, and the distance in the y, or the distance from the y-axis, growing by a scale factor greater than 1. So again, greater than 1 if k is between 0 and 1. So what we have here is a horizontal stretch. So when we have the y-axis that goes like this, we're stretching horizontally. So outwards, we're getting further and further away from the y-axis. If that k value is, I want to call it a fraction, but not a fraction. It's between 0 and 1. So like, for example, if you have a fraction 5 over 4, which is 1.25, well, that's a stretch because it's greater than 1. So when I say fraction, I put that in quotations. So fraction. You can write that down. Okay, and that just means like a decimal. Okay, now compression. So what is a compression? This is a transformation which results in the distance from the x-axis. So again, x-axis, I'll do it over here. Okay, we're going to get closer and closer to the x-axis if our a value is that fraction, right? If our a value is between 0 and 1. We have a vertical compression. And remember, this k value, this is going to be our backward value, okay? We're going to go horizontal compression if k is greater than 1. Okay, so in other words, let's see this hands-on. Okay, the graph of the function, so if we graph g at x equals a f at x, this would be our original. Okay, it's vertically stretched by a factor of a when a is greater than 1. That means it's getting stretched. It's going away from the x-axis. Away from x-axis. Okay, and it's vertically compressed by a factor of a when it's between 0 and 1. So in that case, it's getting closer to the x-axis. And I think with some of our graphs, what happens is, like when we just see two graphs, we can either view it as vertical or horizontal, depending on what we're using as our reference. If we're using as our x-axis or our y-axis as our reference. Okay, so the original would be possibly here. Okay, and the graph g at x equals fk. So the k again inside of the bracket with this x. This is gonna lie to us. Okay, so whatever this looks like, it's gonna be backward. So there's actually a stretch if it's like our fraction for, and again I write fraction in quotation marks. So it's gonna be a stretch if it's a fraction, which gives us this wider one. Okay, going away from the y-axis. And it's going to be a compression if it's greater than 1. So that's going toward the y-axis. Okay, so we're going to use mapping notation. Okay, mapping notations for reflections. If it's a vertical stretch or a vertical compression, what that's doing is it's affecting the y-coordinate, right? It's stretching it up and down. So since it affects the y, we're going to actually multiply every single y coordinate from the original by that a value. Okay, and remember, k is backwards, k lies. So if we have the k value inside of the bracket with the x, that's going to affect the x coordinate. But we're not going to multiply the x's by k. We're actually going to multiply the x's by 1 over k. Okay, so for our mapping notation, we have xy, and the x is going to map on to 1 over kx. So the reason why we have 1 over k is, for example, if the k value, if what we see, so k value is what we see in the equation, okay? If that is a 3, well, we know that it's actually not a stretch, so we can't multiply by 3. So what we're doing is we're taking the reciprocal. We're going 1 over 3, okay? For the opposite example, for example, if we had 1 over 5 is our k value, okay? So we would still be like, this is a horizontal stretch by a factor of 5. And the way we get that is by saying, well, we're going to multiply every x by 1 over k. In this case, we're multiplying by 1 over 5. Okay? A lot of students don't like this. This is okay. We're going to take it back to like elementary school, and we're going to say, well, what is 1 divided by 1 over 5? That's just 1 multiplied by the reciprocal. Remember, we can't divide fractions, so we just multiply by the reciprocal, which is just 5. So that's how we get 5x. Okay, that's basically how we flip it. If we take the reciprocal of something, aka 1 over k, all we do is flip the number. Okay, and how that affects the x is you multiply every x by like the 1 over k. So the reciprocal. Remember, x lies. Okay, and then ay, that's just direct. Multiply every single y by that a value as it is how you see it. Okay, so we are going to start with parabolas. Okay, given the graph f at x, write an equation to represent each of the following and state the mapping notation. Then sketch each graph and state the domain and the range. Okay, so we know that this is going to be x squared. Okay, y equals x squared. We're going to do a vertical stretch by a factor of 2. So what happens is our f at x is going to be 2x squared. We know if we're stretching vertically, we're not going to affect the x's. We're only going to affect the y's. And guys, the y is easy. You just multiply it by 2. Okay, so I'm going to rewrite all of these x's as they are, just to set up my question. I know they're not changing because I don't have a transformation on them. Now I'm going to take every single y value and I'm going to multiply it by 2, right? 2 times the y value. So I get 82028. Okay, and I'm going to go ahead and graph this. So -2 and 8, -1 and 2, 8. Okay, and then this blue one, y equals 2x squared. Okay, now the next one, vertically compressed by a factor of 1/3. So vertically, that's the easy one again. Okay, that's going to be 1/3 x squared. Okay, so we're not going to touch the x's again. We're just going to take every single y value and multiply by 1/3. So 1/3 of the y's. Okay, again, because there's no transformation on x is just the same, we're just going to write out -2, -1, 0, 1, 2. Now let's take every single y value and multiply it by 1/3. So we get 4 over 3, 1 over 3, 0, 1 over 3, 4 over 3. And let's plot. Okay. So we can see here that when we talk about vertical stretches and compressions, if it's compressed vertically, the green is closer to the x-axis than the original is, right? And the blue is getting even further away because that's a stretch. So the blue, a vertical stretch, is getting further away from the x-axis. Okay, now we're going to talk about horizontal stretches and compressions on this parabola. Okay, so this is our original parabola, y equals x squared. And now, what are we going to get for the equation if it's horizontally stretched by a factor of 3? Okay, so we know that it's going, so since it's stretched, it's going to look opposite in the equation. Okay, so this is like direct, like the way you would say it. We can make a little note. The way we would say it is like the direct way. Okay, what's backwards is the equation. So the equation would be, so instead of 3, it would be 1/3 x squared. Okay, so since it's a stretch by a factor of 3, we're going to multiply every single x value by 3, and the y's we're going to leave the same. So we can go down this entire y column, and we can just copy out 4, 1, 0, 1, 4. Okay, and then multiply all of the x values by 3. Okay, so negative 6 and 4, negative 3 and 1, 0, 0, 3, 1, and then 6, 1, 2, 3, 4. Okay, so this is going to be our y equals 1/3 x squared. Okay, on the flip side, horizontally compressed by a factor of 1/3. So we know a compression is going to look like it should have been stretched, right? It's going to be the opposite. So we have 3x, and then that's squared. So what we're going to do is we're going to multiply every single x term by 1/3 because it's compressed, and we're going to leave the y's as it is. So our y values, 4, 1, 0, 1, 4. We're just going to leave them. Okay, and let's take 1/3 of the x. Negative 2 over 3, negative 1 over 3, 0, 1 over 3, 2 over 3. Negative 1/3 and 1. And then negative 2/3 and 4. Wow, that's like very, very vertical here. Okay, so horizontally, we just got closer and closer to that y-axis. Okay, now let's revisit, and I think we have to do domain and range. So state the domain, so we did the mapping, we sketched, now we state the domain and range. So for these ones, domain and range, XER, and then the range, y is an element of the real number system, y is going to be greater than or equal to 0. Remember, this is part of our vertex, and our vertex didn't change. So this domain and range actually applies to both of these. It's the exact same thing. Okay, and the domain and range here, again, the vertex didn't change. So domain is x is an element of the real number system. Okay, they still both go to negative infinity and to infinity. They stretch to the right and to the left forever. And like the starting point, quote unquote starting point for the y's is 0. Oh, so y is going to be greater than or equal to 0. And it opens up. Okay, question 2. F at x equals root x. Let's rewrite root x as a function that is vertically stretched by a factor of 3. Okay, so again, vertically, This is more like the mindless one where we just put the number in front and we write the function. Okay, so this is an easy one. It affects the y. So we're going to write, for the mapping notation, we're going to write the x's stay as they are, and we're going to multiply every single y term by 3. So again, write all the x's as they are, and every single y coordinate, we're going to multiply these by 3. So 0, 3, 6, 9. 0, 3, 6, 9. Okay, and we're going to graph that. So 0, 0, 1, 3, 4, 6, 9, 9. And we're going to label our graph. This is going to be f at x equals 3 root x. Okay, next one. Vertically compressed by a factor of 1/4. Okay, so the vertical one, again, is like the easier one because as soon as you see 1/4, there's no debate. You just write 1/4. Okay, so we're going to have f at x equals 1/4 root x. So our mapping notation, the x's are not going to change, but every single y coordinate is going to be multiplied by 1/4. So let's write the x's out, 0, 1, 4, 9. Okay, and then take every y value and multiply them by 1/4. So we get 0, 1/4, 2/4, which is a half. We can write 2/4 or like a half, and then 3/4. So on the graph, 0, 0, 1 1/4, 4 1/2, and 3 3/4. Oh, 9 3/4. I'll make that bigger. Okay. And then this is going to be f at x equals 1/4 root x. Okay. And when we're doing vertical stretches or compressions, we can see that the blue is further away from the x-axis and the green is going more toward the x-axis than the original. Okay. So again, there were no translations on this graph. They were just stretched. So the domain and the range of these two graphs are actually going to be the same. Okay, we're going to start at this. Remember, like I kind of call it like a fake vertex as though it's like a parabola on the side. Okay, and the graph like starts at 0, 0 here. Okay, and the x values go to infinity and the y values go to infinity as well. So x is an element of the real number system such that x is greater than or equal to 0. And for the range, y is an element of the real number system such that y is greater than or equal to 0. Okay. Next one, we're going to do horizontal stretches and compressions, okay, on the root function. So horizontally, whatever you would like talk about, so this is a stretch by 3. In the equation, it's going to look opposite. So in this case, if you think it's going to be a stretch, it's going to look like a compression, right? It's 1 over k. So 1/3 x, root of 1/3 x. This time, when we do the mapping notation, it's directly as it is, as we would talk about it. So since it's a stretch on the x's, we've stretched the x's, we multiply them by 3, the y's stay the same. So it's easy to fill out the y's, 0, 1, 2, 3. That's easy. Now, we're going to take every single x value here in the original graph, the parent function, the base function, and whatever you want to call it, and we're going to multiply all of these by 3. So 0, 3, 4 times 3 is 12, 9 times 3, 27. And we're going to graph these. So I get 0, 0, 3, 1, 12, 2, 27, 3. Okay, and then this is f at x equals a third x. So again, we're stretching by 3, so we're getting further and further away from the y-axis. Okay, and the last one, a horizontal compression by a factor of a half. So remember, however we would talk about it, it's only going to look different in the equation. Okay, it's not going to look different in the mapping, only in the equation. So we're going to have root 2x. Remember, that's 1 over k. So our x values are all going to be compressed by a half, so we're going to half them. And our y values are not going to change. So write down the y values just to get everything started. Okay, and we're going to half every single x. So half of 0 is 0, half of 1 is a half of 4 is 2, half of 9, it's 9 halves, or like 4.5. Okay, so we have 0, 0, a half and 1, 2 and 2, 4.5 and 3. Oops, I'm going to do f at x. Use that function notation we learned. Okay, so we can see with this one that we're getting is a compression because we're getting closer to the y-axis. Now for domain and range, I always set up my domain and range. X is an element of the real number system such that, and y is an element of the real number system such that. And these two are going to be the same because we're going to have like the same starting point, which is 0, 0. There's no reflections on these, so they're going to increase to infinity in the x and then direction, and then they're going to increase to infinity in the y direction. So simply x is greater than or equal to 0, and then y is greater than or equal to 0. Okay, 3a, f at x equals 1 over x. So now we're going to take a look at the rational function. So if this were to be vertically stretched by a factor of 3, what this means is it's going to look one of two ways. It's going to look 3 times like a half, like that. But if we were to simplify this, it's just simply 3 over x. So whatever this numerator is, let's go 3 over x. So whatever this numerator is, that's going to be the vertical stretch. Vertical stretch, again, only affects the y's. So the x's are going to stay as is, and the y's are going to multiply by 3. So let's write the x's, -1 and 1. Okay, and for the y's, -3 and 3. Because there are no movements, like translations, so no translations, so the horizontal asymptote and the vertical asymptotes do not change. Okay, and therefore, when we get into it, the domain and range won't change. Okay, so we're just going to rewrite y equals 0, x equals 0. Okay, so the horizontal and vertical asymptotes, I'm not going to redraw, but I will label them. So this is y equals 0. Okay, because it goes through the y-axis, you can call it y equals 0, and this one goes through the x-axis, right? Goes through up and down like this x-axis, so to call it x equals 0. So I'm going to graph -1 and -3, and then 1 and 3. And I just know this from like, it's kind of reflected here, but I just know that there's going to be like 3, 1, so it's going to be approximate like this. And there's going to be -3, -1. And the more you do, the more you're going to be comfortable with it. But regardless, you can just plot it with this point, swoop it around, okay? And then just don't let it intersect the x or the y, or like the horizontal or vertical asymptotes. Okay? Now, if it's vertically compressed by a factor of 1/2, how is that going to look? So vertically compressed is going to be 1/2 times 1 over x. So I'm actually going to highlight this. I'm going to leave it like this so that we actually treat this as a vertical compression. But if you were to multiply these across, what is this equivalent to? Let's think about this. Well, what transformation is around the x? So in this case, for 1 over x, a vertical compression is equivalent to, well, what's going on here? That's a horizontal compression. They're actually equivalent, because this would be a horizontal compression by 1/2. But we're going to leave it as vertical. I'm going to leave it so that the equation looks like this. And I'm going to write the x's as is, and all of the y's are going to multiply by 1/2. Okay, so 1/2 of -1 is -1/2. 1/2 of 1 is 1/2. Horizontal and vertical asymptotes don't change unless there are translations. So -1, -1/2, it's going to be in here. Okay, so we're going to have 2 points, and then we're going to have 1.5, 1.5. And even if you just plot 1 point, it's fine. It's as long as it goes through that 1 point, we're good. And that's why we only use -1 and 1 as the x values. Okay, so domain and range. X is an element of the real number system and Y is an element of the real number system. And as a recap, X is going to hit every number except for the vertical asymptote. And Y is going to hit every number, except for the horizontal asymptote. Okay, I personally don't even have those memorized. I just have to look at a graph, or I just have to sketch it on the side of my paper. So x is not going to equal 0, y is not going to equal 0. Okay, now the rational function horizontally stretched by a factor of 4. So what I'm saying is also going to happen in mapping. The only place where it's backwards is the actual equation. So horizontally stretched by a factor of 4, what we're going to get is we're going to get 1 over, well, it's horizontally stretched, so it's going to look like a fraction. So we can write 1 over 4x in the denominator. 1 over 4x. Okay, however, I'm going to show you this equivalence. So if we had 1 divided by 1 over 4x, we're going to flip that. So 1 times 4x. Well, you know what? Leave that off. 1 divided by 1 over 4, 1 times 4 is actually 4. So we can see here that a horizontal stretch, because if this is just a 4, it's going to look like 4 over that original x. A horizontal stretch and a vertical stretch are actually equivalent. But you don't need to do this for this question. You can just write it as formally a horizontal stretch. So since we're stretching horizontally in the literal form, we're going to multiply every x by 4 and then leave the y's as it is. So we're going to go -1 and 1. Those are going to stay. We're going to stretch this by 4 and stretch this by 4. So we get -4 and 4, and the horizontal and vertical asymptotes don't change. Okay, so I'm just going to make a dotted lines where the vertical and horizontal asymptotes are, and I'm labeling them x equals 0 and y equals 0. And now I'm just going to plot my 2 points, -4, -1. And then 4, 1. And guys, for me, as long as it's in the correct quadrant, like say for example, quadrant 1, quadrant 2, quadrant 3, quadrant 4, as long as the graphs are in the correct quadrant, they don't cross the asymptotes and they approach the asymptotes, I'm okay with this drawing. Okay, but just know like the quadrants are only, like they're going to change if there are translations. Okay, now horizontally compressed. So again, in the equation is the only thing that looks backwards. So if it's horizontally compressed, it's going to look like it's going to stretch. So 1 over 3x. But every x is going to be compressed, so multiply them by a third. The y's are going to stay the same. So write out all the y's. Now compress every single x. So we have a third, or negative a third, and a third. Okay, and the vertical and horizontal asymptotes don't change. So I'm going to plot -1, -1. No, lying. Negative a third, -1, and a third, and 1. Okay, as long as it goes through that one point, we're in the right quadrants. And then we can do domain and range. Since there are no translations, this is going to be for both of them, by the way. Since there are no translations, x does not equal 0, y does not equal 0. That's coming straight from the horizontal and vertical asymptotes. Okay, example 4, given the graph of f at x, so this is again like a random graph, that's why we just call it like, oh, the function. Okay, write an equation to represent each of the following transformations and state the mapping notation. Okay, then we're going to state 4 points on f at x, and then we're going to sketch each graph. Well, the original is done for us already, so we're going to sketch the transform graph and state the domain and range. Okay, so vertically stretched by a factor of 3, what we're going to get is 3 times whatever f at x is. So the x's are going to stay the same, and the y's are going to multiply by 3. Okay, so let's point out like either the endpoints or like a turning point here. So we get -5, 3. Okay, we get -2, 3 as well. -2, 3. Okay, 3, -2. And we get 5, 0. Okay, and we're going to use this base graph for all of them here. So we're going to leave all the x's as they are. So -5, -3, -2, 3, 5. And we're going to take every single y value and multiply it by 3. So 9, 9, -6, 0. 9, 9, -6, 0. That's just quick mental math. So now let's plot it. -5, 9. -2, 9, 3, -6, and 5, 0. Now we're going to do the same thing, except for we're going to compress it by a factor of a half. So how that would look in the equation is 1/2 of f at x. So we're going to take every x and just graph it, but every y we're going to half it. So let's list the original points, -5, 3, and these points are going to be the same all the way down. Okay, so for all 4 examples. Okay, the x's we're going to keep, so -5, -2, 3, and 5. And this time, we're going to half all of the y values. Oh, I need a y in there. So 3 halves is 1.5. 3 halves is 1.5. A half of -2 is -1, and a half of 0 is 0. So -5, 1.5, 1.5, 3, -1, and then 5, 0. Okay, so the domain and range are going to be different in these ones. So domain, we only did a vertical stretch, so nothing actually affected the domain. So we're going to go from -5 to 5 for each of them. Okay, so x is an element of the real number system. such that x is between -5 and 5. Okay? So I'll put it up here. Now, because we changed the vertical components, the ranges are going to be different. So for the blue one, we're going to go from 9 all the way down to -6. Okay, so y is going to be an element in the real number system such that y is going to be between -6 and 9. Okay, and for the purple one, we're going to go, the top number is 1/2 and the bottom number is -1. Sorry, 1.5, I meant. Y is an element of the real number system such that y is going to go from -1 to 1.5. Okay, and we can actually see that in this column. Okay, so we're going to do the same ones, but horizontal. Deep green. Okay, horizontally stretched by a factor of 2. So since it's stretched by 2 in the equation, it's going to look like it's a compression. But in the mapping, we're definitely going to stretch it by 2. So multiplying by every x value by 2. Okay, and -5, 3, -2, 3, 3, -2, 5, 0. Okay, so multiply every x by 2, so I get -10, -4, 6, 10, and the y stay the same. 3, 3, -2, 0. Okay, so let's plot that. -10, 3, -4, 3, 6, -2, and then 10, 0. Okay, so the x's going up and down we didn't change. So we're going to go from like the 3 to the -2. So x is going to be between -2 and 3. Now the y's are going to go from -10 to 10. Did that backwards. X's are -10 to 10. Y's are -2 to 3. Okay, and this time, like again, the y's aren't changing. We're just horizontally stretching it. Okay, now if we have a horizontal compression by 1/3, in the equation, it's going to look like a 3. But in the mapping, we're definitely going to 1/3 all of the x's. Okay, so -5, 3, -2, 3, 3, -2, 5, 0. So 1/3 of -5 is -5 over 3. 1/3 of -2 is -2 over 3. We get 3 over 3, which is 1. Right, these are the x's. And then 5/3. And the y values we keep the same. 3, 3, -2, 0. Okay, again, because we're keeping the y values the same, our range is not going to change. So -5/3, 3 will be here. -2/3, 3, it's going to be here. 1 and -2. 5/3 and 0. This time I'm not really going to look at my graph for the numbers. I'm going to really rely on my table of values, okay? So x is going to be between 2 numbers and y is going to be between 2 numbers. What I'm going to do, just because like these are really not nice numbers, I'm going to pick out the largest and the smallest x value. So the smallest x value is -5 over 3, and the largest x value is 5 over 3. Now for the y's, the largest x value, or the smallest x value, y value is -2, and the largest y value is 3. Okay, it may be difficult to correspond with a graph because they're partial numbers, like they're fractions.